Produced and created by the Mindsticks Foundation Trust. When you look at this vintage electric fan with its blade spinning, you're actually watching a hidden interaction at work. Flowing electric current creates a magnetic field, and that unseen push and pull is exactly what drives the machine. Understanding how to control that invisible magnetic effect is the blueprint engineers use to turn raw electricity into continuous physical motion. This diagram outlines Maxwell's right-hand thumb rule. It gives us a reliable way to find the direction of the magnetic field created by a straight current-carrying wire. If you imagine holding the wire in your right hand, your thumb points in the direction of the electric current, and your curled fingers trace the exact circular path of the magnetic field. If we take that same straight piece of wire and bend it into a circular loop, as seen here at the bottom, those magnetic lines compress. They form tight concentric circles around the wire, which intensifies the magnetic pull right through the center of the loop. Now, look at this cross-section of a solenoid. By coiling the wire many times like a spring, we align all those individual circular fields into uniform parallel lines. The entire coil now behaves exactly like a standard bar magnet, complete with a distinct north and south pole. By simply changing the physical shape of the wire, we can concentrate, direct, and turn these magnetic fields on and off whenever we need them. We can also run this interaction in reverse. This setup shows what happens when you place a current-carrying wire inside an existing magnetic field. The horseshoe magnet and the wire's own field interact, exerting a physical force on the copper, causing it to bend. To predict wire movement, we use Fleming's left-hand rule. Align 3 fingers at 90-degree angles. Your index matches the magnetic field, your middle matches the current, and your thumb points to the resulting physical force. Let's test this. Point your left index finger right, matching a north to south field. Point your middle finger at the screen, matching the current. Based on your thumb, which way is the force pushing the wire? The answer is downward. This 3-finger alignment is the link that translates invisible electromagnetic theory into a predictable physical force you can see and measure. That predictable physical movement is the basis of the electric motor. Looking at this schematic, we can see the core components at play: 2 heavy permanent magnets, a rectangular copper loop spanning the gap, and a set of split rings at the base. If we trace the circuit on the left side, the current flows from point A to B. Applying Fleming's left-hand rule, we calculate that a firm downward force is applied to this specific branch. Over on the right side, the current travels in the opposite direction, from C to D. The left-hand rule shows the physical force pointing upward. Together, this downward and upward push initiates a counterclockwise rotation. Those opposing forces kickstart the spin. But there's a mechanical catch. Left like this, the simple loop fails exactly halfway through its first rotation. Once the AB branch reaches the right side, the downward force remains downward. It will violently resist the upward climb, snapping the loop back and forth instead of allowing it to spin continuously. To fix this stalling problem, engineers added a split-ring commutator. This close-up view highlights 2 distinct halves of a conductive ring, labeled X and Y, making contact with 2 stationary carbon brushes, E and F. At every half turn, the gap in the split rings passes the stationary brushes, swapping their contact points with the power source. This instantly reverses the internal current, ensuring the physical force keeps pushing in the same circular direction. That gap in the metal rings is the mechanical intervention taking a twitching piece of copper wire and turning it into a reliable engine. With the commutator in place, electrical energy feeds into the loop, creating a magnetic field that pushes against the permanent magnets. The loop spins, continually flipping its current at every half turn, converting electricity directly into continuous mechanical work. To keep your calculations straight, use the right-hand thumb rule when you need to map out the magnetic field generated by a wire. Switch to Fleming's left-hand rule when you need to predict the physical force applied to that wire. We've seen that moving electricity can create a magnetic field. In 1831, a scientist named Michael Faraday asked the reverse question: could moving a magnet create an electric current? Faraday's answer to that question bridged the gap between magnetism and electricity, laying the groundwork for the generators and motors that supply our homes and drive the industry we rely on today.